will be talking about part of my DPhil study today, which is assessing the use of protactinium and thorium to understand climate-related processes in the ocean. So I thought I'd start with this figure here you all might be familiar with. CO2 has been rising in the atmosphere. CO2 has been rising in the atmosphere due to the release of fossil fuel carbon, and a dramatic increase was recorded in the late 1800s during the Industrial Revolution, and has since then continued into the 21st century here. And this has led to lots of climatic and environmental problems, especially in recent years. For instance, on land, rising CO2 has caused global warming and sea level rise that put thousands of coastal cities, like Venice in this picture here, at the risk of being claimed by the sea. And in the ocean, rising CO2 has caused seawater to become more acidic, leading to the bleaching of coral reef and death of marine organisms that depend on it. So this life form the bottom of our food chain. So eventually our life on Earth will be threatened. So basically that's a problem that I'm interested in this study. And as a chemical oceanography student, I'd really like to understand the ocean's role in looking into these problems and dealing with them. So why should we think about the ocean? The primary reason that the ocean contains 50 times more carbon than the atmosphere does. And as deep ocean, most of the carbon is stored in deep ocean, where deep ocean circulation has a great impact on how much it is stored and for how long. But what I'm going to really focus on in my study is deep ocean circulation and its influence on climate. So what else do we know about deep ocean circulation? This illustration here shows you how deep ocean circulation modulates the heat between the air and the ocean. So this warm surface currents here brings the heat from the tropical areas to high latitudes in the North Atlantic, where the heat is released to the atmosphere. And in this way, these regions are kept ice-free. And then this water becomes sufficiently cold and dense that it sinks to the deep ocean, forming deep ocean circulation flowing southward to the other parts of the Atlantic. And this water is often called North Atlantic deep water. If this water becomes sluggish or totally shuts down, less heat would be, the heat transfer would stop. So less heat will be transported and released to the atmosphere in high latitude regions. As a result, these regions will be very cold and has a variable climate, like the one happened 20,000 years ago, which we call last glacial maximum. That is the peak of the last ice age. If you couldn't quite picture what it was like 20,000 years ago, one of my favorite animations, Ice Age, would help. So hopefully I have shown you that deep ocean circulation can store large amounts of CO2 and also modulate the heat between the ocean and atmosphere. So for these reasons, deep ocean circulation is a very important component in the Earth climate system and has been a focus of many climate studies for decades. And one of the many ways to study it is through oceanic traces, which are elements and the isotopes that dissolve in the ocean. So this is also the approach that I will be taking in this study. And these two elements down here in the periodic table are the main focus of this study. So how do we think protactinium and thorium work as an ocean circulation tracer? This figure here will give you a general idea. So protactinium and thorium are produced in the ocean at a constant ratio and removed by marine particles that sink down into the sediment. If no factors other than the production and the removal came into play, protactinium and thorium should be removed in sediment at a constant ratio as they are produced in seawater and everywhere should be the same. However, another factor, deep ocean circulation, is at work. In Atlantic Ocean, for example, deep ocean circulation transports sticky protactinium out of North Atlantic. As a result, protactinium to thorium ratios increase. as deep ocean circulation flows southward from the North Atlantic to South Atlantic, leading to high protecting thorium ratios in the South Atlantic, but low in North Atlantic. So a simple way to put it is that the presence of deep ocean circulation leads to low protecting ion to thorium ratios in the North Atlantic. The stronger this circulation gets, the lower protecting ratio that we're going to get. So based on this theory, studies like this one here use protecting ion to thorium ratios in the North Atlantic sediment to indicate the variations in deep ocean circulation and the climate changes in the past 20,000 years. So for instance, these relatively higher values here were used to indicate weakening deep ocean circulation, and they were coincident with the cold climate last glacial maximum 20,000 years ago. And these these relatively lower values here are used to link the stronger deep ocean circulation to the warmer climate in more recent Holocene period, which still continues to the present. So studies like this have demonstrated that protecting ion to thorium can be used as a very powerful tool to study the relationship between deep ocean circulation and the climate changes. However, the robustness of its application is questioned due to a lack of understanding of protecting ion and thorium in various ocean basins, which is limited by a very sparse database. So black dots here on this map show you all the existing thorium protecting ion data in the Atlantic when I started this work in 2010. We've got some measures here in the North Atlantic and some here in the eastern side of the South Atlantic, but rather sparse data here in the Western Basin. So expanding the data coverage on this map has become the motivation that led me to undertake the Oceanographic expedition in 2011. So with a group of scientists from the Netherlands and the States, I went to this research course as part of an international oceanographic survey, GEOTRACES program in February 2011 aboard the British Royal Research Ship James, which is on this picture here. So we sailed from Punta Arenas down here, all the way north across the equator, and then ended in Las Palmas after 36 days at sea. So in the next few slides, I'm going to show you what I actually did and what the science was like during the cruise. So basically, my job at sea is to collect seawater samples. And the major tool to do this is these bottles. It is called a rosette, and it has a series of bottles around the outside of it. And these bottles are in fact tubes with leads at both sides of them. So when you put these bottles into seawater to collect samples, both leads have to be kept open so that the water could go through the tube. And at a certain depth, you send out signal through the wire to open the trigger that shuts the bottle. And after all the water depths are sampled, these should be properly shut, and then you can withdraw the rosette back to the ship. So this is desperate people queuing for samples when the rosette's back on ship. And this is me collecting seawater samples. Because protactinium and thorium are very low level in seawater, I have to collect large volumes of samples of up to 10 liters for each water depth, so that I have got enough to measure. By the end of the cruise, I have collected 900 kilos of seawater to play with back in Oxford. So because of this, I was accused of stealing too much water from King Neptune and the equatorial baptism. And then got the punishment, like I had my face shaved, kissing a dead fish, and getting trashed by the food waste from a couple of days ago. You can tell from my face that it was no fun at all, but this guy seemed quite enjoyed it. So the other reward that days of nights on something at the sea is that you get to capture some amazing moments of the ocean, like these cute guys sunbathing on a platform, or a beautiful sunrise, or a sunset. It is really difficult to stop taking pictures of them. And at the end of the cruise, everyone has got like several gigabytes of photos on their cameras to bring home with them. So back in Oxford, I have these seawater samples measured for protactinium and thorium. Since they are, as I mentioned earlier, thorium and protactinium are very low level in seawater, which is 10 to minus 15 grams per kilogram of seawater. So it is extremely difficult to measure, and I had to control it a lot. So that means I have to use special techniques and work in an environment that is metal-free. And they have to be measured on this super sensitive mass spectrometer. So far I have shown you what I'm interested in this study and what I have done to look into them. Now I'm going to show you some results. So these results are published earlier this year in one of the core journals in Earth Sciences. So these figures here are vertical profiles of thorium and protactinium in the water column. As you can see, they have very similar behavior in the upper water column, but have very distinctive features in the deep water. This one, thorium increases toward the bottom, while protactinium are quite constant. If I put all the profiles that I've obtained from this course together, we've got figures like this, showing you the distribution of thorium and protactinium along a southwestern Atlantic section between the equator and 6 degrees south. These gray shades here represent sea floor, and the black contour shows you the water depth where southward flowing North Atlantic deep water is present. And red colors are high concentrations, coke colors are low concentration. So the main feature of these figures is that thorium and protactinium do not change much between stations at the same water depth. So if we bring these features together, we get a figure like this, the ratio of protactinium and thorium along the same section. So I don't have time to show you all of the findings, but I'm going to show you one of them. So just to remind you, the theory tells us that protactinium to thorium ratios should increase from the north of the Atlantic to the south. From our observation, however, we don't see such pattern. In fact, protactinium to thorium ratios are almost the same from the north of the section to the south of the section. So this is one of those, it is fresh moment in research, in scientific research, because it is surprising because it contradicts with our conventional view of protactinium and thorium in the ocean. It even suggests that protactinium to thorium ratios do not work the way we expect them to be at the deep ocean circulation tracer, at least not in the southwest Atlantic. And previous data, like the one I showed you earlier, are therefore required to be reinterpreted. So just to wrap up the talk, so findings like this are the major reward for going out to sea and setting up challenging analytical techniques in the lab. And in the end, we are able to map out some major patterns in the ocean, like this one here. With this information, we are able to improve or even correct our understanding of how things work in the ocean based on what we actually observe and see, rather than what we think they should. And all of this motivates us to keep doing the research like this, not only from a purely intellectual point of view, but also to deal with societal problems like climate change and understand the shape of this graph that I showed you at the very beginning of this talk. So thank you very much for attention, and I'd also like to thank my supervisors, Professor Kim Henderson and Alex Thomas, who have given me tremendous support during my DPhil study. And I'd like to thank China Oxford Scholarship Fund to financially support me for 2 consecutive years. And thanks to Wolfson and Susan for putting this together, this first ever conference together. Thank you.
So we now have time for some questions.
I have a question, actually. Feifei, the studies look like they've been concentrated in the Atlantic. Are there any plans to have studies to look at the situation in the Pacific Ocean, where there's been considerable seismic activity, in addition to, let's say, the Fukushima nuclear disaster with the water pollution in unmeasured levels? So what is the plans for that? Any studies to be done?
So actually, facility is a very understudied area because lots of reasons. Like first, it is very big, so it is really difficult to go to this central area of the Pacific, and also because not many countries can go that area because So actually, only Chinese ships Japanese ships and some American ships can go to Pacific, but the other like British ships couldn't really do such in that area. But these are very interesting areas to look into, and because of this GeoTraces program, many countries are now working together so that they can look into some areas which are not studied before.
So I hope China-Oxford collaboration might be a way of allowing Oxford to reach that region then. So any other questions? If no, thank you, Feifei.